To begin our examination of the MySQL architecture, we're going to take a bird's eye view, a very high-level view of the categories within which the different components of the architecture reside. And that first category contains the connection and authentication manager, as well as the thread manager. We're going to look at each of these components in much more detail. But again, to get an understanding of the high-level framework of the MySQL architecture, we're going to group these into categories for now. So the next step after getting a connection to the database server is to parse the query. And as we'll see, this is actually a fairly complex process. But in this case, logically, the next step is the parser components. Once the query is parsed, we have two possibilities. Either the query has already been seen by the MySQL database, in which case it's going to be stored in the cache, or the query is going to be passed to the optimizer so that a query tree, the path of access to the data, can be developed. Then one of the components within this optimizer category is going to execute that query against the storage engine. Recall that the MySQL architecture allows us to plug different storage engines into the database architecture, and we can mix those storage engines for our application. And as we'll see, there is a good selection of different types of storage engines which we can select from or combine to best serve our application. So with this high-level framework in mind, let's take a step down and look at each of the components within these categories. So in our manager category, where the connection and the authentication and the thread assignment occurs, there are actually many different components that perform those tasks. There is an authentication component. That component is responsible for ensuring the security of any attempted connection. This is where a user and their password is authenticated for connection to the MySQL database. And that connection can either be a local connection, so from the same machine, or it can be a remote connection over a network to the machine on which the MySQL database resides. And there are two components for dealing with those connections, either local client connection or remote client connections. Each are managed by those respective components. And once we have that connection, the dispatcher and scheduler is responsible for ensuring that the connection has a thread on which the work can be accomplished. So things that are important to note about this category of functionality provided by MySQL is that when we connect to the MySQL database, our connection gets a separate thread of execution. Now, this process has been greatly improved in the latest version of MySQL 5.6 to provide us a much more stable and reliable concurrent thread pool. When our connection is assigned a thread, we're also assigned resources for the query execution. And these resources are those that are needed for management of the query and the return data from the database. So the read buffer, the sort buffer, the temp table, these are resources that are dynamically assigned to our connection thread and can be administered by the DBA when necessary for optimizing the performance. And MySQL is very flexible in its connection protocols. Any program using a variety of different connection protocols, ODBC, JDBC, PHP connection, can utilize the services of the MySQL database. In addition, there are several administrative tools, either open source or fee-based, that can connect either locally or remotely to any MySQL database. That's important to note that the remote connections occur over TCP/IP, while the local connections can be accomplished over either TCP/IP, if you're in a Linux environment, the Unix sockets, shared memory, and if you're in Windows environment, pipes, NT pipes. So once we've gotten our connection and we've passed our query into the MySQL environment, we have a thread with dynamically allocated resources for execution of that query. The query is then passed to the parser. The parser category has several components that comprise this parse function within the MySQL architecture. The first step is to parse the query, and parsing the query is ensuring that the SQL statements are legal SQL statements, that the keywords are correct, that the arguments passed to the statement are in the order in which the SQL statement expects them, and so on. And then the authorization of that query, whether or not that query has the authority, has the permissions to access the resources that it needs to execute. And the query may be rewritten based on the outcome of the parsing function and the optimizer function. So the query optimizer is responsible for examining the statistics on the data within the database and all of the possible paths to access the data required by the query, finding the best path and building a, quote, query tree, unquote, to execute that query based on this developed best path. Then the query is passed to the plan executor. The plan executor is responsible, obviously, for executing the query plan, the query tree, as it was developed by the optimizer, returning the data then to the user. Then there's a utility component that executes data definition language statements and other utility statements within the MySQL environment. In summary, the parser performs both a lexical and a syntactic analysis of the query. The lexical analysis identifies the tokens and the other values or variables within the statement, and the syntactic analysis validates that the tokens and the values make sense, that is, that they are valid SQL statements. Then the query optimizer finds the best execution plan for the query. This can be problematic because the query optimizer will continue to search for a plan until it finds what it believes is the best plan. And the search is exhaustive. So at times, as administrators, we need to guide the query optimizer to limit this search in order to optimize performance. So the next level in our architectural framework is the selectable storage engines. Of the storage engines, they each have their own implementation of a lock manager. This is the component that's responsible for protecting the data to ensure the consistency of the data when multiple users are connected to the database. The buffer manager is responsible for moving data from the disk to the memories so that required data is in memory to respond to queries. The log manager is responsible for the durability of any changes to the database. So as we said, the MySQL storage engine is a pluggable component in the architecture. There are several different storage engines that can be used either individually or in combination to meet the requirements of our application. Two of the most common storage engines are the InnoDB and the MyISAM storage engines. But there are others. There's an in-memory storage engine, there's the NDB or cluster storage engine, there's the comma-separated values storage engines, and there's others on top of those. But again, the two most common, especially for transactional systems, the most common and only ACID-compliant storage engine is the InnoDB engine. And the other common storage engine is the MyISAM. So in this course, we're going to focus on the InnoDB engine, and we will demonstrate how to mix the engines, especially the InnoDB and the memory storage engine, to optimize the performance of a MySQL installation, but we're not going to examine in detail any of the other storage engines. One of the other very important considerations when selecting a storage engine is not only the requirements of the application, but performance implications. Again, if the application is transactional and we're trying to adhere to the ACID principles, then we only have one choice, and that's the InnoDB storage engine. However, one of the other considerations is the locking granularity, which refers to when data is being accessed, whether or not during that access the row on which we're acting is locked, or whether the entire table is locked. This has a profound impact on the concurrency permitted within the database. So just as a summary, again, we're going to focus on the InnoDB, and we will demonstrate the combination of the InnoDB and the memory storage engines in an application. But our focus is going to be on transactional application support using the InnoDB storage engine. The final category that we want to examine is the utilities in the shared components category. This category has a lot of components that manage the MySQL environment, including the component that manages the replication of data. So putting this all together, we can see, in contrast to our high-level view of the MySQL architecture, that the MySQL database system is actually an amazingly complex system that's composed of, in this case, high-level components within these categories. And if we took another step down into this architecture, we'd see that even these components are made up of subcomponents, and so on. This is another characteristic of the MySQL database management system that makes it unique. And notice that the query optimizer is highlighted in this diagram, because much of the other functionality provided by MySQL, and in fact other database management systems like SQL Server or Oracle, are fairly standard. Authentication of users is a fairly standard function within any database system, in fact, any application system. The parsing, the lexical and syntactic analysis of queries, a fairly standard function. However, the gold, the most important part of any database system is its brains in how it can find the best path to the data. That's the function of the query optimizer. How can I use the statistical information within the database to determine the best, fastest path to the data that I need? That's the function of the query optimizer. And every database system, whether MySQL, SQL Server, Postgres, Oracle, and DB2, and so on, this is where the rubber meets the road in the query optimizer. So as a summary, the MySQL architecture is unique in that it offers this pluggable storage engine architecture where we can combine different storage engines, assigning specific data to a storage engine to meet the needs of our application. And that no matter which storage engine we select to support our application, the interface for using that storage engine is consistent across all of the storage engines. And the MySQL database management system, beyond the uniqueness provided by the pluggable storage engine architecture, provides an amazingly robust implementation because of its modularity. So where can we install MySQL? Well, again, MySQL is available for Windows, it's available for Macintosh, it's available for Linux, Solaris, and so on. Now, we're going to demonstrate the installation of MySQL on Windows and Linux. However, going forward, after we demonstrate the installation, going forward, all of our demonstrations will be on the Linux platform. The reason for this is that the Linux platform is the preferred platform in the real world for the implementation of the MySQL database. So we want to be in that realm for the rest of our demonstrations. When we demonstrate the installation, we're going to see that we have options for the version of MySQL that we want to install. The MySQL community maintains older releases for download. However, we're going to select the most recent stable release. And furthermore, we are not going to download and build source releases. We're going to download and install the binary release for the targeted operating systems. So let's go look at this installation process.